Hello. Is this working? No. Thank you. Well, hello. Sorry, now it works a lot more. Just a brief announcement or something that maybe you want to pay attention. So, you know, the Hubble Space Telescope is a nice telescope, but it's getting old, and there are maybe hopes that it can be pushed in the 30s. One concern is that it's re-entering the atmosphere, but maybe you have heard Swift is they are attempting to boost its orbit. Maybe it's a good omen for other instruments like this one. But for this to happen, which is a very difficult, it's a very complicated operation for Hubble, clearly there has to be a very strong community interest. And so NASA's STScI has asked people to present white papers to show cases that Hubble will be good for in the 2030s. So this has happened. Maybe some of you sent, maybe not, but anyway, STScI also recognized that writing a white paper is a bit of a commitment in the life of a busy professor astronomers. So they also say there is a new opportunity to chip in that is with a simpler form. Basically, they call science pitches, and they ask for 1-2 paragraphs about topics, themes that Hubble could help in the 2030s. So I think they want really to receive a strong support from the community to show that it's worth investing resources to prolong the life. So there is this online form, a QR code. There is also a link. And just one thing, I think it would be nice. We are at a conference. Many of us are presenting talks. A few of us are listening to them. Like whenever you see, oh look, this would be Hubble would be perfect to push this. Maybe you can follow some of the talks and think, or the ones that you are giving yourself, and say like, this is worth, I want to do it again and better with Hubble. So this could become a science pitch. It's not meant to be a very big commitment, just basically a Google form. And one thing that I noticed that in the report from the white papers that they already received, they say, many science cases were received, including blah, 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 and transient multi-messenger astrophysics was not mentioned. So I think it's actually important that this community tries to push our case. So that's it. I'll shut up.
15th July. Be quick because it's the 15th July, the deadline.
Yes.
Okay, so I'm going to take advantage of the slot that there was available to speak to you about an instrument opportunity that is coming along at VLT. So VLT is looking for new instruments for having at the observatory beyond 2030s. So as you've already seen, in the 2030s, there's going to be quite a lot of things going on for transient astronomy and not so transient astronomy. There's going to be a lot of instrumentation going on. Rubin is already working. We're going to have neutrino observatories, maybe more gravitational waves, ELT working. SVOM and Einstein Probe will still be flying. Hopefully, Swift will still be flying also. The Nancy Roman Space Telescope also. So there's going to be a lot of stuff going on. So we need to find out what the VLT role is going to be at that time. So as I said, there's a call for white papers. This is a funded call. So they're going to be funding for multiple instrument concepts to be funded with 10 million euros of hardware, just hardware, for several projects. And our plan is to submit something for the call deadline on the 15th of January 27. And the phase A would start a year later. So as you know very well, one of the instruments devoted to transients at VLT is Extragalactic. We are part of the team that built Extragalactic, which is a triple arm shell spectrograph covering from the UV to the near infrared. And it was highly successful. It was meant for transients. It was designed for transients, but it's been, as you very well know, very used by many other science communities. So it's an excellent instrument, but it has some limitations. Namely, there's a limited acquisition imaging. We have only a visible camera. There's no infrared, so we are missing high redshift events or highly obscured events that do not show an optical counterpart. We have 3 slits, so there's some misalignment between the slits that needs to be corrected every time we point, so we lose a bit of time in acquisition. The near infrared has some thermal issues, which lead us to sometimes not use the K-band because it contaminates the other bands. So there are some things that can be improved. You can always improve efficiency of detectors and coatings and optics, thanks to the 20 years of difference that the instruments would have. So what do we look for in transient science? Well, that's the one that we have to cherish, that very important photon that we don't want to miss. Not a single one photon we should miss. So what are we looking for? We're looking for multiband imaging, broadband spectroscopy. If we can at high time resolution, polarimetry is also something that we're very interested, although it's been perhaps less exploited, both in imaging and spectroscopy. And once you're at it, why not make it integral field? So as I mentioned, the team that we're getting together is starting from the team that built X-Shooter. We are also part of the team that conceived the Scorpio instrument that is being built at Gemini. People from Hypercam, from NTE, from SOX, from Colibri. So we are building a community there to be able to have the best possible instrument. So up to now, we are at 3 possible concepts that we're discussing. And as you'll see later, we want to have some input from your side in order to decide what is more valuable, what we want to do. The first option will be a high time resolution multiband imager, something like Hypercam has at GDC, but including most likely infrared imaging also. So that would be something like of 8 or 9 bands observing simultaneously. So from the U band to the K band or something similar with very high time resolution. If you have just the imaging, you have the advantage that you can have the highest possible throughput. We're thinking of a field of view of around 3 arc minutes. And there might be the possibility to even do multiband polarimetry. So we're working on that. So that builds on the heritage of Hypercam, which has been a very successful instrument at GDC. It's got some advantages and weaknesses. So it's got a very high throughput and the best time resolution capabilities. It would be affordable probably within the budget. But it has, of course, limited capabilities, and with the deep multiband surveys that they're already in place, like the Rubin telescope is providing, and other telescopes, is going to be not so competitive for some cases. And of course, that includes no spectroscopy. Another way would be to go for a super X-Shooter, trying to improve some of the deficiencies of X-Shooter, and perhaps going to a higher spectral resolution. So the second option would be a visible to near infrared shell spectrograph, probably the same coverage as X-Shooter, but trying to reduce the noise using different technology detectors, go to around 30,000 resolution with very low noise detectors, kind of photon counting. So even if you go to high resolution, it does not mean that you cannot observe fainter targets because you can co-add that. That works quite reasonably well for the optical. For the near infrared, it's a bit more complicated. It is easy to do spectropolarimetry in such an instrument, and we would have a multiband acquisition camera, at least a camera in optical and another one in infrared, probably multiple ones, something more like NTE has with perhaps 3 cameras. This has a high spectral resolution, so that's a strength that allows for detailed studies. The multiband acquisition that we don't have in X-Shooter, the spectropolarimetry, but it's a bit more limited in the sense that we have to go to brighter targets that we've got to study very well, but you have limited targets. We have limited simultaneous bands as compared to the previous idea, and probably a more limited time resolution. The third concept is more like the Scorpio instrument that is being built at Gemini. It would be a multiband imager and spectrograph. So this is probably an 8 or 9 band imager and spectrograph. So as compared, I don't know how many of you know about the Scorpio instrument that's being built at Gemini. That's an 8 band GRIZYJHK. At VLT, we had the option to go for U band also because of the coatings of the telescope that are different in Gemini and VLT. The spectroscopy would be at around a resolution of 4,000, which allows us to look in between the skylines of the infrared but keeps the resolution low enough to go to the fainter targets. That's a common focal plane. So the focal plane is in a cryostat, and it's a single focal plane with a single slit for all the arms. With a retractable ADC, we for sure can do spectropolarimetry. We are still working on the imaging polarimetry. And we could have, using the single focal plane, an integral field unit. So this is getting the heritage from several of these instruments. So as I say, this is based on the Scorpio concept that is actually being built. It's being integrated in Gemini right now, but it has some capabilities in addition. So this has most of the scientific ambitions that we have considered. It has a higher throughput than the shell concept, both the next shooter or that the high resolution spectra would have. So we would have more potential targets. We can go for deeper, fainter targets. We would have the polarimetry and the IFU unit. However, it is an expensive instrument, so not as efficient as the hypercam concept. So it would be hard to fill it within the budget that ESO is giving. So we would have to look for further funding possibilities. And as I mentioned, there's also the other instrument built at Gemini, so at Gemini South. So we would be in some way competing with it, even if we have some additional things that Scorpio would not be doing. So that's a bit of the specifications. And in order to get a bit more information from your side, as I mentioned, we have prepared a survey that we would like you to participate in. Cristina may say a word about that. She's been taking care of the scientific part.
Yes, hello everyone. I'm Cristina Thune. As Antonia said, I'm responsible for the science part of these instrument concepts that we have been discussing in a very small team in the past month since the conference at ESO. And so we have prepared a little survey because we have been discussing a lot and we cannot agree on what we actually want to do. So what you do, if you don't know what to do, you ask more people. So that's what we want to do here. We prepared a little Google form. Don't be afraid, you don't have to remember all the instrument concepts that we just presented. We want to have a bit more detail. Do you want more spectral resolution, less spectral resolution? Are you actually interested in something like polarimetry or IFUs? And in order to get a bit of overview, we invite you, all of you, to please fill in that survey. Either you now take a picture of the QR code, or we're also going to send you all an email. And please feel free also to distribute that survey to your colleagues that are not here, because we want to have as many opinions as possible. Thank you.
Thank you.
Let's continue with the conference. So then, oh yeah, let's do one question because we're a little behind. So.
No, the question is, this morning I've been contacted by someone that is at the SPIE and asked me if I knew something about a new instrument that they are proposing for keck that is called Z-Shooter. So are you aware of this? Do you know?
Yes. So I think it's a higher resolution. It's more towards the shell concept. Okay. But I don't know the details. But yeah, keck is also working on KEC is working on an instrument for transients, broadband spectrograph. GDC also got funding for building a new similar instrument aimed at transients. So it's something that different telescopes are looking into. So yeah, apparently it's an attractive concept.
Thanks.
Awesome, great. Let's thank the speakers again. And I'll call Mattias Lazda. Is Mattias around?
Yeah, I'm online.
Okay, it's wow. I was freaking out for a second.
Good.
How do I here?
Awesome.
And I will authorize you. Share.
Thank you so much.
Chris.
All right. Can you guys see this all right?
Yes.
Awesome. And I'm just gonna hide floating. All right, and I'm assuming this is all sharing as normal.
Yes, that
Awesome.
works perfect.
Thank you so much.
Awesome. Take it over. Thank you so much.
All right. Well, thank you so much to the organizers for allowing remote participation. I'm super sorry that I can't be there. I am Mattias Lazda. I am a PhD student at the University of Toronto in Canada. And today I'll be presenting on the summary of the results of a campaign to monitor a particular supernova with VLBI, so very long baseline interferometry, and the implications on our observations. All right. So today's talk is going to largely focus on neutron stars, and in particular, trying to identify and study newborn neutron stars formed via core collapse. So I imagine many of you are familiar with neutron stars, and in this case, they come in a large number of flavors. We know that they emerge from or are formed via core collapse, evidenced by the fact that we image them directly within evolving supernova remnants, like the one on the left. But they also come in different styles as well, where you have your pulsars, which have this beamed emission, which is used for a lot of interesting extragalactic or galactic transient astronomy, and also magnetars. So these have grown in particular, or have grown in popularity in recent years, in particular due to their relationship or likely relation to fast radio bursts, which you'll hear a lot about in this conference, I imagine. But one thing that's kind of open in the air about this sample of neutron stars is that we don't really have a well-defined sample of young neutron stars. And when I say young, I'm talking about on the order of decades. And that's just because the rate at which core collapse happen within our own universe or within our own local universe, in particular within our own galaxy, is quite rare. And so we have to extend our sample to nearby galaxies if we want to actually build up a sample and look for multi-wavelength evidence for extragalactic neutron stars. And so the supernova that I'm going to be focusing on here is supernova 2012 AU, which was an explosion that was first detected in 2012. It's at a distance of 23 megaparsecs approximately, and it stood out from its kind of class of type 1b supernovae, in particular because of its energetics. It was atypically energetic, so reaching 10 to the 52 ergs, which is about an order of magnitude larger, or on the order of an order of magnitude larger than kind of similar supernovae in the same subclass. And the reason that it kind of grew or became very interesting is that its optical evolution was very atypical. In particular, the early evolution was both weird, but then also the late time evolution started to exhibit these forbidden emission lines that weren't really consistent with the typical supernova model for this type of class of supernova. And so this prompted a paper in 2018 led by Danny that claimed that there was evidence for a young pulsar wind nebula at the origin that was emerging from this extragalactic supernova. And for those that aren't familiar, just what a pulsar wind nebula is, kind of the best example that I can give you is the Crab pulsar wind nebula. And it's the result of when you have a pulsar, it injects energy into the surrounding environment when it forms as it spins down. And when that energy is confined to a dense region surrounding the neutron star, it generates these beautiful winds that you can see. And so the question is that we have this supernova that's been claimed at the origin of 2012 AU. And the reason that this is notable, if it were to be true, is that within our own galaxy, we do have a sample of these pulsar winds. There's over 200 galactic sources known, but they all reside within our own galaxy, and they're all centuries to millennia old. And so up until this point, we've had to look at systems that are hundreds to thousands of years old and try to infer the properties of the central neutron star at formation using theoretical models, but without direct observations of these things when they're originally formed. So if we could confirm that this source is actually a pulsar wind nebula, we could try to infer, we can get a first direct constraint on the formation properties of the neutron star. So coming back to 2012 AU, while so far we've focused on the optical observations, in the radio, the evolution at early times was nothing really weird. It kind of behaved exactly as you'd expect for supernovas of this class. But what did stand out was the evolution of the supernova at late times. And so after 5 years, around the time that this pulsar wind nebula paper came out, claiming that there was evidence of a young neutron star, there was also detected rebrightening in the radio. And just based off of the plot on the right-hand side, you can see that this was you're reaching peak fluxes at late times that are on par with the original supernova explosion. So it's as if another supernova went off, but in this case, there was no optical supernova associated with it. So it's something else that's driving this late time radio emission. And so there's a number, supernova 2012 AU is not the only supernova that's exhibiting this kind of late-time radio emission. There is a rare subclass of probably on the order of 10 to 20 of these known supernovae that have this radio emission. And there's kind of a number of models that have been put forth to justify or try to explain what's going on. So one of these models is indeed an emerging pulsar wind, and I'll talk about that a bit more in detail after. But there's other models to consider as well, such as shock interaction with the circumstellar medium. So as your supernova ejecta plows into the surrounding stellar, whatever's left over from the original supernova, or prior to the explosion, it can generate radiosynchrotron emission that is detected at late times. But you can also get an off-axis launched jet, which at early times it's beamed away from us on Earth, but at late times can be detected. So this is, I imagine, there's also going to be some talks on GRB afterglows and off-axis GRBs, so stick around for those. But in this case, I'm going to focus mostly on the first model, a young pulsar wind, given that there's optical favoring of it, and I don't have enough time to talk about the other two. But if you're interested, feel free to ask me afterwards. And so in order to actually try to disentangle between each of these three models, we set out on a campaign to image this source using very long baseline interferometry, which is the same technique that's used to image supermassive black holes. But in this case, we're doing it at lower frequencies. So our observations span between 2020 and 2026, and we observed a source at 5 gigahertz and 23 gigahertz. And in the best case in which we had the highest angular resolution, we were able to achieve roughly 0.5 milliarc second angular resolution, which is able to probe down to scales at the distance of the source of about 0.01 parsecs. And so to jump right into the conclusion or to the results of these observations, what we found is that after imaging the source repeated times, the source remained compact in all of our observations. So that implies that in all of our observations, what we got were upper limits on the source size as a function of time. And since the source, we know the distance again, this was placing constraints of the source down to 0.045 parsecs at roughly 3,000 days. And since we also had repeated measurements, we were able to place constraints on the proper motion of the source. So how quickly is it propagating across the sky? And although it was challenging to get this due to where the source is located on the sky, we were able to place an upper limit of roughly 0.36 C, which implied that the source was roughly stationary within uncertainties and was able to be used to rule out certain models, for example, off-axis jets, which have predictions on how fast that ejecta should be moving, or that jet should be moving. And so with all that, we can now take these observations, which in this case, we have these radii as a function of time or upper limits on the radii, and ask, is this consistent with what you'd expect for a young pulsar wind system or a young neutron star system? And so to kind of, before I jump into what the implications are, the basic picture is if you have, in the standard model is you have an expanding shock wave, which is your ejecta left over from the original supernova. And interior to that, you have an evolving pulsar wind that is expanding into the interior of that ejecta. And the dynamics of this system, so how quickly this radius is evolving as a function of time, is a complex function of kind of the initial energy budget of the central neutron star, as well as the properties of the surrounding environment. So there's a lot of assumptions that you need to make, but there's a broad consistency that is able to reproduce late time evolution of systems that are thousands of years old. And so we use those models to see if we can place constraints on the formation properties of these systems. And so when we do this, these are kind of the main results that we get. Now, I know for those that don't do pulsar science and that have never seen a pulsar or a PP dot diagram, this means absolutely nothing. And so because I'll just kind of, it's a super busy plot, but I'll generalize and kind of point out the main things that I want to highlight. So first, if you're looking at this is effectively constraining what the initial starting parameters of your central pulsar are. So it's period and period derivative. And what we found is that if the source that we're seeing at the associated with 2012 AU is driven by a pulsar, it can't be driven by a millisecond pulsar because there's just insufficient energy to generate a synchrotron nebula. We also rule out a large number of just kind of your average pulsars that have, again, insufficient energy and magnetic field strengths to generate the synchrotron nebula. But what we find is that kind of the allowable parameter space that we find is entirely consistent with what we see with systems that do have young pulsar winds or that are embedded in supernova remnants. So these typically are systems like the Crab, where they're a couple hundred to thousands of years old. Now, these systems have evolved. And so the prediction from optical is somewhere in here from the original discovery paper, and it remains entirely consistent with our VLBI observations. And so the conclusion that we drew from our paper was that if you were to assume that the source is, or that the radio source is an emerging pulsar wind, then it's thus far entirely consistent with theoretical expectations, along with predictions from optical. Now, the fun doesn't stop there, because when you think about the source, or the fact that the source is evolving, we expect that the pulsar wind should be expanding rapidly with time. And so we basically all simple theoretical models predict that over the next couple of years, the source should become resolvable. And so with future VLBI observations, in particular with global, where you combine radio telescopes across the globe and increase your antenna participation, then we should have sufficient angular resolution to probe and really constrain these theoretical models and see if we need to adjust it. And so as the final note before I finish, I just want to highlight kind of a recent result that came out from a collaborator of mine who's been looking at this source with VLA SEDs, as well as a broadband from radio all the way up to X-ray. And they've also been monitoring this source for over 5 years and have found that the source is really well described by theoretical expectations for a young pulsar wind, although more detailed analysis is going to be needed to fully constrain and test some of these models and do proper fits to them. And so again, to conclude and to emphasize that the work that I'm presenting here, while our observations focused on the VLBI observations, there's kind of a growing body of literature that's now starting from 2013 all the way up until now that really is starting to paint a picture that is inconsistent with other models that invoke, for example, shock interaction with CSMs, but that thus far are entirely consistent with what you'd expect for a system that has a young neutron star at this extragalactic distance. And so we argue that this makes 2012 AU one of the most promising candidates for an extragalactic pulsar wind, which would allow us to place constraints on the formation properties of the neutron star, study its evolution, and see if any theoretical information can be gleaned from this young system. And so with that, I will leave it there, and I'm happy to take any questions. Thank you so much.
Awesome. Thank you, Mattia. Any questions for speaker? There's one question in the corner of the room. The last person in the room. Hidden.
Hi, Mattias. Great talk. It's Lauren here.
Hey, Lauren.
So you say this is the most promising candidate, but and you said about how you I love the narrative. What other ways are there that we can try and search for these objects? Are radio surveys, are they a promising source of candidates, or are there just going to be too many false positives in there?
Yeah, I think it's difficult. So I think the hallmark is that we just want to identify a larger sample of sources that have rebrightened at late times, ideally many years post collapse. So I think that the timescales over which you're expecting this to occur is just on the order of 10 years. Things below that are more consistent with just gradual expansion of the shock wave into a supernova, into some leftover CSM. But if it remains to identify, I think just taking all this supernovae that we're observing now in the optical and waiting on the order of 10 years and following them up and just going for the ones that are within a reasonable distance so that we can actually resolve it with VLBI. Of course, the closer the better, but we don't always have that freedom. But yeah, effectively just waiting and having radio surveys is useful. Like VLAS is kind of what prompted this. This was, I think, back in 2019 or 2020, there was a VLAS paper that showed that the reason that we detected the radio rebrightening in the first place was driven by these radio surveys of historical supernovae. So I would encourage people to continue doing that so that we can keep identifying these systems and studying them in detail.
Awesome. Thank you.
Great. Any other questions for Mattia? There's another question over there. They just want to make Antonio run.
Hello, nice talk. I had a query about potential FRB detection, which I did see in the paper.
Yeah.
So is it a really promising source for FRBs at this stage? Because I also understand the emission can maybe optically get absorbed due to the supernova or pulsar wind nebula. So I would like to know some insight on this.
Yeah, great question. So I think right now, So if we assume that FRBs are primarily detected at gigahertz, for sub-gigahertz, or around less than or equal to 1.4 gigahertz, the SEDs suggest right now that that would just be self-absorbed. You could, in principle, like make some argument that it can break through, but overall, the SEDs predict that any emission that's generated with interior to the supernova, the pulsar wind, or whatever is driving this, would be self-absorbed by the ejecta. But the SED is evolving. The peak of the SED is cascading to lower frequencies right now. It'll just take a couple more years, I think. I think there's, I would check Eli's paper. He has a time scale over which the optically thin, or the peak in the SED is cascading to lower frequencies. But I think in our estimate, we say roughly a couple years, or 10 at most. But yes, it is a very promising candidate to do follow-up targeted observations of FRBs.
Awesome, great. Sadly, we don't have time for more questions, so let's thank the speaker.
Thank you very much.
And let's move on to the next talk, which is by James.
Yes, I'm
Mattia,
also
you're still
online.
sharing.
Sorry, my computer's frozen.
Great, awesome. Oh no. Can I? Okay, you go ahead. I don't know French,
Yeah.
so.
Yeah, I do know French,
Salut,
but
ça va? Je m'appelle Thomas.
I should work.
That's
no,
all I know.
Why doesn't it work?
Il n'a pas le droit de partager.
Je pense que c'est peut-être. Can you share?
Is this fine?
Great, awesome.
It works. Yeah.
Okay, perfect. Hi, everyone. Sorry I couldn't make it to be in the meeting in person. Okay, so let's just get started. So today I'm going to be talking to you about a triple humped radio light curve that we see in a type 1c broadline supernova. A lot of this work that I'll be presenting today is done by a student at University of Toronto, Sam Lacadas scale. So let's jump into it. All right, so the first thing I want to talk about is what these 1c broadline supernovas are and why we're so interested in them. So the 1c broadline supernova are those that come from a Wolf-Rayet progenitor with their helium and hydrogen envelopes stripped, and the broad lines from their spectra indicates that they have these very, very high expansion velocities. And so with these high expansion velocities, what we can infer from that is that there must be the kinetic energy that's in the ejector must be in some part driven by a central engine, and this is why at least some subset of GRBs show an association with these 1c broadline supernova. So in 1998, you had this very famous event, GRB 980425, with an association, a spatial association with a supernova 1998 BW, which is the standard supernova that 1c broadline supernova we compare to these days. And this is the spectrum that of the 1c broadline 1998 BW supernova, but this was just a spatial association. Then in 2003, we indeed saw this smoking gun association between the GRBs and the 1c broadline supernova here, and we see this clear non-thermal spectrum evolve over time to this 1c broadline like spectrum. And so one of the questions then is, why is it that we don't always see a GRB with these 1c broadline systems? Is it perhaps that sometimes the center engine is not powerful enough to power a jet, so that it's choked within its stellar vestige? And can this be completely explained by metallicity properties or not? So indeed, perhaps there is a diversity of outcomes in these central engine-driven supernovas, and perhaps that could also be due to viewing angle effects. So in a possible unified scenario for 1C broadline supernova and GRBs, FXTs, and so forth, the different phenomena that we may be seeing may just be produced by different viewing angles. So radio studies actually provide a very promising method to understand the diversity of these outcomes in these central engine-driven supernovas. So for example, on the left, what we can infer from the peak of the radio spectrum are properties such as the density and the radius of the ejector, and from that you can infer also the velocity of the outflows and identify and try to understand those that are driven by some central engine. So for example, here, this one over here is a famous supernova, SN 2009 BB, a central engine supernova with velocities that are much higher than typical other 1C broadline supernovas and very close to the velocities of GRBs. So lately, there's also been a lot of work that was, for example, discussed in the previous talk on identifying rebrightening events. So with these large-scale radio surveys, such as with ASCAP and VLA, we've been identifying these rebrightening, and this rebrightening could be, for example, due to the presence of an off-axis jet, or perhaps a pulse wind nebula, as indicated in the previous talk, or something like an enhancement in the CSM. So today, I'm just going to quickly talk about one of the most remarkable radio-like curves we've been seeing in 1C broadline supernova, and this belongs to supernova 22XXF. It is this 1C broadline supernova with the hydrogen helium lines stripped and broad lines indicating of velocities up to 14,000 kilometers per second. And this is the discovery image, and you can see this supernova occurring over here. So the supernova has a very beautiful light curve and extremely densely sampled spectra. And you can see that in excess to the standard radioactive decay, you see an excess over here from maybe 40 to 100 days. And this excess corresponds also to the emergence of these narrow lines in the spectra. And so this was proposed to indicate that there is some confined CSM interaction go on producing this early excess. And so the radio light curves show something quite remarkably a similar rebrightening at the radio wavelengths. And you have the red over here is an optical light curve from ZTF, where the other light curves are radio light curves. And you can see in radio light curves, it follows a standard power law decay, and then at the time of the optical rebrightening, there's also a mirror rebrightening in the radio, and one of the questions is are they related? Just very quickly, this is where XSF lies on the plot from before. You can see it lies somewhere between the other one BC supernova and the very energetic ones that are often associated with GRBs. So what we determined from analyzing the radio light curves from this initial rebrightening is the inferred radius is actually incompatible with that from the optical from the CSM that was inferred from the optical light curve and spectrum, and it's by an order of magnitude. And perhaps this optical enhancement, the CSM that's causing this could be some asymmetric CSM that's free absorbed at the radio wavelengths. So one of the cool things about this supernova is that it's actually what we call a trinidal supernova. And the reason why we say this is because it also has a secondary brightening linked to 3 humps. And this is what we see in this late light curves over here. We have this late rebrightening. And very interestingly, I think this is probably the first supernova we see this in. There is a spectral inversion. The radio spectrum shifts from an optically thin spectrum to optically thick spectrum. In this last spectrum over here, there's also some indication of some flattening that we saw initially, and we think that this flattening is not actually there, but it's related to some data problems now. But the flattening is very interesting. It has implications on perhaps whether there is an off-axis jet. And so these were the scenarios that we considered as was producing this enhancement. And as I mentioned before, the flattening that we saw seems like a Newton power 1/3 power loss level that's very typical for a GRB afterglow, where you have the ordering of the injection frequency above the self-absorption frequency. But when we threw some VLBI at it, the size of the source constrained by the VLBI observations is more than an order of magnitude more than what we would expect from a GRB jet expanding, and even at a off-axis angle. And so what this leaves us with is perhaps it would be a possible nebula or some CSM enhancements. So as we were saying before, we had some data issues here, but what we saw is essentially the shifting of the self-absorption frequency to these higher frequencies, and if we interpret this under the CSM enhancement scenario, what this is likely saying is we have a much higher the enhancement in the CSM is about 600 times denser, and actually the radius of the CSM is much further in, order of magnitude further into the explosion site than the first rebrightening the earlier radio light curve. And so this could be actually due to some asymmetric CSM, perhaps even due to what led to the narrow lines that we saw in the optical spectrum. So there is still this possible nebula scenario to be investigated in more detail. So we don't exactly rule that out at this moment. And so this is where this is at right now. So I'll leave on this slide some concluding remarks, and I'll take any questions.
Thank you, James. Questions for James? Dan has one here.
So you said if you want this to be interpreted as CSM enhancement, the density has to increase by a factor of several hundred. Did I understand that right?
Yes, that's correct.
So how does one achieve that in a progenitor system plausbly, do you think?
So this enhancement is actually closer in. So it's a strange argument. Give me a moment. So what I'm suggesting here is that this enhancement over here is 600 times denser than what's seen in the radio light curves here, but the radio light curves here seem to be produced by a CSM shell that's located further out. So it's natural that when you're located further in, the CSM density is actually higher. So we're actually seeing the CSM that's further in later.
Awesome. Thank you. Any more questions for James? Well, if not, let's thank James once again.
All right, thank you.
And let's move on to the next part of the conference, which is another news and... No, sorry. There's Melissa here with us. Sorry, my bad. Melissa is going to talk about supernovae as cosmic architects. So
That's removed. Okay, I have to share this. I guess we okay. Let me put in screen first. Can I? Is that so much? Control that.
Hi, everyone. My name is Melissa Shahbandeh. I'm an STScI fellow, and today I'm going to tell you about the role supernovae play as key dust producers of early universe. Do I use this? So why do we care about dust? I'm sure you all have heard that dust is the building block of the universe. So dust is behind star formation, planet formation, pretty much everything that we see out there. Dust is what forms these objects. So until very recently, it was believed that AGB stars were the main producers of dust in the early universe. But then JWST came along, and we found these massive dust reservoirs in high redshift galaxies. For example, here on the right, what I'm showing you is this galaxy at Z14 that was only a few million years post-Big Bang, and it hosts huge dust reservoirs. But as you know, AGB stars take forever, hundreds of millions of years to produce enough dust to explain these dust reservoirs. So they cannot sort of describe why these red galaxies at Z14 have these huge amount of dust. So what is the alternative scenario is supernovae. Core collapse supernovae are pretty massive stars that die pretty young, about a few 100,000 years. So these supernovae or these objects can explain why we can see these massive dust reservoirs in the early universe. And what I do is trying to actually confirm that these supernovae are the key dust producers of dust in the early universe. So we believe that there are two groups of supernovae among all the other ones that probably are the best candidates to explain these massive dust reservoirs. One of those is strip envelope supernovae, since these supernovae die pretty young and they're on the side of the most massive stars. This plot that I'm showing you on the right, it comes from Carniani et al. 2024. This group studied these two Z14 galaxies, and by their study, they showed that in order to host these massive dust reservoirs, you require supernova that is younger than 5 mega-year old. And strip envelope supernovae are a great candidate to explain these Z14 galaxies that are pretty dusty. The second group of supernovae that we believe contribute to these massive reservoirs of dust are interacting supernovae or type 2N. Why? Because if we look at their observations with Spitzer in the past 2 decades, the plot on the right shows the brightness of all different types of supernovae over time. And as you can see, there's this group that we're showing with black dots on the top right that stays pretty bright and gets brighter as time goes on. And one way to explain that is that these objects are getting redder as they get older, and probably what is happening is that they are accumulating dust or heating dust that is around them. So that's why this is the other group of supernovae that we focused on studying to understand why they stay bright decades post-explosion. So now what I have here is a sort of a cartoonish view of what happens when the ejecta of these supernovae interacts with the circumstellar material out there. This is sort of me trying to explain why we believe these interacting supernovae, or sometimes strip envelope supernovae that have lost their outer layers, can accumulate a huge amount of dust. So type 2N supernovae, as you know, they interact with their CSM, and strip envelope supernovae also have lost a lot of their outer layers. So when the ejecta of these supernovae hits the CSM and starts interacting with this CSM, what happens is that this is something we call cold dense shell, that they create this envelope or this shell that is protected from the reverse shock of the supernova, which is what people believe that is the main reason supernovae are not dust producers, because the reverse shock destroys the dust that was formed. But the cold dense shell, what it does is that it protects the material or the dust that forms from being destroyed by the reverse shock. Another thing is that as the time goes on and the ejecta interacts with this shell, it deposits more material into that shell and it cools down. So you start to condense particles into dust grains, and over time you can accumulate a lot of dust. So let's say we detect dust. How can we understand it, and how can this help us understand this whole cosmic dust main question? So what we do, let's say we have these supernovae and we detect dust in them. Well, the first thing that we're after is to understand if this dust is pre-existing or is newly formed. Because if it's pre-existing, it does not support the fact that these supernovae are the key dust producers in the early universe. They could just be heating the dust. So it's very important to understand if the dust that we observe is newly formed. Another thing that we want to know is how much dust do they produce, or how much do they contribute to the cosmic dust budget in the universe. We also can understand their geometry. We can probe the ejecta. We can understand the characteristics of the dust. And we can also find out what molecules are there and the composition or species of different types of dust that these supernovae host or form. So what I have here is sort of a diagram that I'm trying to explain how dust forms in supernovae. So let's say from the left, if we have a strip envelope supernova or a type 2N Bombian, around 70 to 100 days, we can start to see these features or these molecules that we believe they contribute to cooling the ejecta of supernovae to temperatures at which dust can form. So it's very important when we detect these molecules, because we know that they are starting to cool down the ejecta. The two main molecules that I'm showing here, there are more, but these two, CO and SIO, these are strong diatomic molecules that have really cool and great capacity, vibration capacity, that can cool the ejecta pretty quick without them being destroyed. So let's say we find these molecules, we can observe their evolution, and they stay there for a couple hundred days. We expect after a couple hundred days, if we have these molecules, to start seeing the dust features showing up, for example, silicate emissions. Since the ejecta is now cool enough to have dust formation happening in the supernova. So today since we don't have enough time, I'm gonna focus on old dusty supernovae, or the ones that we already have seen dust signatures early on. So I'm gonna show you a few examples to show the variety of dust that we observed in these supernovae and what we learn. In order to do that, as you know, that if we want to understand dust, we need to go to the IR, and we have JWST that shows us these amazing data, which we are using here. So one of the objects that we observed in cycle 1, JWST, is the supernova 2004 ET. It's a type 2P supernova. So it's not as massive as strip envelope or type 2N. However, if you look at the image on the left, this is a stacked image of different filters taken with a MIRI. As you can see, about 2 decades post-explosion, it's pretty bright, which even without doing any sort of studying, we know that it must be hosting a lot of dust, and that's why it still is bright and red. So on the right, what I'm showing you is the different models that we use to model the SED of the supernova. So this was besides 87A, which you all know it's very dusty and has this dust ring. What we found is that in this 2004 ET supernova, we find about 0.04 solar mass of dust, which is pretty huge. Besides 87A, this was the most dust mass that we found in any supernova ever. And the reason I'm showing you these different models is that to show that we tried all these different compositions, such as silicate, carbon, alumina, to explain this. And for this one, we found that it's either optically thick silicate that we don't see the silicate features, or it's made of mostly carbon. Another example of a type 2P that I'm showing you here is to show how different they can be, even though this supernova 2017 EAW that is younger was also a type 2P, and the ground-based data showed that it's pretty similar to 04 ET, but as you can see here in the IR, we can fit it pretty well with a silicate model. So now I'm going to show you type 2N supernova, two examples. So what I have here is 2005 IP, which is the only supernova that had a Spitzer spectrum, and about 2 decades later, we got this JWST spectrum at the bottom. Top left is Spitzer, bottom right is JWST. So the Spitzer one, since that was the only thing we had 3 years post-explosion, what we could explain it with is just the carbon dust, which pretty much looks like a black body, or it could be optically thick silicate. Why? Because it's 3 years post-explosion and we have a lot of dust, we cannot see through the ejecta, so what we see is just a black body emission. But 20 years later, the supernova ejecta has expanded and more dust has formed. And now, using JWST spectrum, we can clearly see these two silicate dust emissions. And what we think is happening is that during this 3-year post-explosion with Spitzer, we had optically thick silicate. We couldn't still see the emissions, but now has expanded, it's optically thin, and we can clearly see these silicate features, but also we found out that there is more dust in the JWST spectrum compared to the Spitzer, meaning that the supernova kept forming dust over the years. I'm not going to get into the details of that, but we use this equation that I'm showing at the top to model the spectrum of this 2005 IP. There were other lines there, but the main result was that we found 0.1 solar mass of dust, which was even more than the type 2P that I showed you earlier. And as you can see, there are two silicate emissions, which means that we have optically thin silicate, and we possibly have a little bit of carbon on the bluer side to explain that sort of emission around 5 to 7 micron. And based on a sort of a combination of different methods that we use, we found out that this dust is newly formed. A major one is that we look at the hydrogen line in the optical, if it's asymmetrical. We also, when we model the supernova SED, we also try to get a radius for the dust. So if this radius is far out there, then we know it's probably pre-existing dust and the supernova is only heating it. But if it's at a distance that closer to the core, then we can tell that, oh, this supernova must be forming new dust. There is another supernova that I'm showing you. This is also type 2N, more recent than that, but 2010 JL, which is about 15 years old. As you can see, this spectrum, they are pretty much very similar in terms of ground-based data, but the spectrum looks very different in the IR. By the way, these are all from the same program. So what we did is to model the spectrum of 2010 JL, we tried all these different compositions that I'm showing you on the right. The black curve is the spectrum, the real JWST spectrum, and then these different colored curves are the models that we tried. For example, we tried alumina, we tried carbon, silicate, and we found out that, well, first we needed better models, but also that there are either two things happening. Either we have alumina in the supernova, or we have silicate absorption. What I mean by silicate absorption is that we probably had a lot of carbon in the ejecta of this supernova. It's emitting a lot of light, but we have this cold dense shell outside the carbon layer, which absorbs some of the emission from carbon. Therefore, we see this silicate, can I point? No. So we see this sort of absorption around 10 micron on the plot on the right, which we believe is a silicate absorption. And the dust mass that we found in this supernova is more than the other ones that I've shown you earlier, about 0.2 solar mass. And all these dust masses that I mentioned are the lower limit, meaning this is the minimum. We could have a lot more if we could look at further in the red. And we also found out the dust in this supernova is also newly formed. So my summary is that supernovae seems like we're showing that they are rapid dust factories addressing the high redshift galaxies that are pretty hosty. We found these newly formed dust in the cold dense shell of 2005 IP and 2010 JL. None of these spectra, I have a bunch more, but none of these actually look the same. And when we study them, also, we don't get the same sort of result or pattern. We need more data and we need better models. Thank you so much.
Thank you, Melissa. Questions? I think we have time for just one. So who raised their hands first? Rock, paper, scissors? I'm gonna, yeah, you go first. Two. Yeah. Over there.
Thank you, Melissa, for the very nice talk. I have two questions. One is, how did you constrain the dust geometry, which I couldn't understand? And second is, from the CDS, you expect for 2005 IP that the late spectrum is probably from the CDS and the dust is from there. So don't you expect carbon from CDS? Like, does carbon dust evaporate or destroy at that, if it's coming from the CDS?
I removed that part. Thank you, great question. So what we do is that we calculated the radius for, sorry, I'm gonna do your second question first. We calculated the radius for carbon and silicate, both of them. So carbon seemed to, for the Spitzer and for the JWST spectrum, both carbon radius seem to stay the same. That's why we concluded that it's probably not the cold dense shell because it's not expanding. But then the silicate radius actually become much bigger. However, it wasn't based on all the putting everything together. It wasn't beyond the what would we call the CSM limit, meaning it wasn't the pre-existing. What was your first question? Oh, the geometry. So that depends on what model we use. For example, if I want to calculate the temperature, this temperature is one of the most important ones that we use in our models. You cannot, for example, have a temperature that goes up to 3,000 Kelvin for silicate. So you constrain the temperature for silicate to, let's say, about 1,700 Kelvin, because beyond that, the silicate evaporates. Or for carbon, it's like 1,200. And then for radii, there are these kind of physical or chemical characteristics of these compositions that we use to constrain these parameters. Does that make sense?
Awesome. Let's thank Melissa and I encourage the people that had questions to approach her after the session. Now we're moving into what Daniele is going to chair. It's the news and hot topics, the roundtable on Supernova 2026 GZF. And I think there are slides, right?
Yep. So I invite all the speakers to come down a bit like with the flash talks. So as Antonio has anticipated before, we had left a few slots over the week to discuss topics that would emerge after the formal abstract submission deadline, things that hopefully are of interest of the community. So it is actually my pleasure to have here some of the representative of the papers that have described this event, this EP 260321A, and I mean, I will just, yeah. You think we could all sit down? Yes, why not? I don't know. Sure. Up to you guys.
Do the slides first?
Sure. Okay, let's do the slides. Yeah. So, can I move on? Very good. So maybe some of you noticed that on June 8th, there was a burst of papers on the archive, and this was the concerted submission, of course, from the groups, that several groups, and we have, there were papers by the EP team, by Chen et al., Rastin et al. I'm just reading the names. Connor et al. Brendan is online. He will speak in a minute. Hi, Brendan. Are you there?
I'm here. Hi.
Great. Hello. And last paper by Antonio Martin Carrillo. In addition to these 5 speakers, Huey Sears has agreed to show a preview of her James Webb observations. And just to play in context, this is a slide prepared by Brendan, which shows a bit like this is actually the 3rd closest high energy transients so it's a really unique event where we could be able to carry a lot of very specific measurements. But like I feel I'm speaking too much, and the idea is to convene here the people who actually
keep talking.
Did the work. And please go ahead and add this. Okay, perfect. First speaker will be Wenxiang Li from the Einstein Probe team.
Okay. I will present the EP observation for this target. So the first slide is a timeline. The EP detect the source like about 800 seconds after the transient on-site. And after that, around 200 seconds, the FXT did the autonomous follow-up. And the GCN notice sent out several minutes later. So here, this is the WXT discovery image. And the zoom in image, this is the FXT follow-up image. And here is the optical image. And the EP official circular was sent out about half hours after the event, which publicly sent out. This is the spectral of the X-ray spectral of this event. And the left is the black body fit, and the right is the power law fit. And it can be fitted by the black body as with a temperature of about 0.1 KUE. This is one of the most important parameters we got from the EP observations. And here we have the WXT detection and also the FXT detections. And here there are 2 FXT telescopes, and their counting rate is a little bit different because they use different observing modes. And we have some other parameters, and the temperature decreased a little bit during this phase. I will show another temperature evolution plot. And for the power law fit, it's not very good. If you use a simple power law, it gives unphysical like gamma of about 10. And the author also used the cutoff power law, try to fit the spectrum, and the temperature and the gamma, that is similar. Like the shape of the fit is very similar to the black body function. So basically, they conclude this is the black body is the best fit. And you can see the high energy part is already like disappeared. There's no signal, so they only use the energy between 0.3, 0.4 to 2 keV. Actually, it can reach, like the sensitivity can reach to much higher, but there's no signal. And because there are many photons, so this is the integrated fit, and the spectrum can be divided into different time bins. So the authors divided the FXT and WXT, like the whole spectrum, into 16 segments. And those segments were fitted together, and all of these segments are consistent with the observed black body spectrum. So the prompt emission stays thermal during the evolution. And this is the light curve. The upper panel is the light curve of the EP observation. And here is this shallow blue is the WXT data, and the dark one are the FXT data. The T90 is about 1,700 seconds. And this is the red line is the MC fit to the light curve. And the fitted parameters is here. The uncertainty is around 1%, so I didn't show it. And here is the temperature evolution, the temperature fit. So it goes from 0.13 keV to about 0.11 keV. And the fitted shock breakout radius is about 300 solar mass. And the width of the shell is about 50 solar mass. So it's a CSM shell located at this radius with this width. And if we assume the velocity of the CSM, we can get that this shell was ejected around several weeks before the core collapse. And the CSM mass is about 10 to the minus 4 solar mass, which is very small, because if we get the X-ray energy, and if we assume there's a kind of strong assumption that all the kinetic energy goes into the thermal energy of the CSM. So if we assume that, we get this mass of the CSM. So the final plot is the comparison between this event with the previous two events. So the brightness of these EP events located between these two, and there's no non-thermal tail of this event. So put all this together from the EP prompt emission. This is a thermal X-ray shock breakout event occurred in the CSM shell. This is supported by the soft black body spectrum, and no radio. It's not from this work, but for other works, no radio counterpart, and a large breakout radius. Okay. Thanks.
All right, so I've been asked to do a few minutes summary on the results from Janet Tingman Chen's paper on the same object, specifically highlighting the cool results that are presented in this paper, namely the very early optical counterpart discovery and the precursor activity that was uncovered in pan-stars. So just to again summarize, the images on the top are the science image that was taken from the Leung telescope, the LOT telescope, 1.25 hours after the EP trigger. So this was a very rapid follow-up search for the counterpart. It was identified in the first night, and because it was rapidly identified, many observations were taken with these two Leung telescopes within the first few hours. That's sort of what the figure on the bottom here shows, with the big obnoxious arrow. So there's a bunch of data points here just in GR and I that show that there is some excess here on the order of a few hours to a day after the object exploded. The counterpart was associated with what looks like a blue compact source on top of the galaxy. There was a bit of discussion as to whether this could be some foreground variable star or some foreground thing that's coincident with the object. There's a bunch of discussion on this in the paper. I will not bore you all at 6 p.m. on the details, but if you're curious, you can come and talk about it after. But we're pretty confident that this knot is associated with the host galaxy at a redshift of 0.034. With regards to the light curve fit, this isn't really a fit to the data. This is just a comparison to a model with and without CSM interaction for another similar broadline 1C. And the point is just that to get anywhere near the luminosity you see within a few hours, you need to have CSM interaction. When we studied a bit more the location of the transient, we discovered that if you go back through the baseline observations in pan-stars, there is evidence for significant precursor activity and variability within this region of the host galaxy across the 12 years pre-explosion. So we've studied this in detail and we've looked at it, and it seems pretty robust. It looks like all of this variability is exactly coincident with the transient. So the argument here is that this is linked to some unstable final stage evolution of the star immediately pre-supernova. So the argument here is that some of the variability in the last few years is roughly coincident with the timescale you expect for oxygen burning in a star of this mass. And then the plot on the bottom is just a comparison to other objects that have shown precursor activity. And it looks like this is a bit more extreme, but sort of within the ballpark of what has been seen before. And then finally, just to really hammer home the point that we really do think these things are coincident, this is just a plot that shows the measured centroid of all of the different surveys that have imaged this part of the sky before, and they all measure a centroid for the blue compact source, and then overlaid on that as well in the top is all of the locations measured for the supernova from LSST, from the Leung telescopes from Pan-STARRS, and from all of the precursor activities. And we find that the location is very, very, very consistent across all of these surveys. So we're pretty sure that all of this stuff is spatially and temporally linked.
Hi, everyone. I'm presenting the results from Julian Rasinajat's paper and the ZTF collaboration and kind of a broader collaboration on this work. So I'll be focusing mostly on the optical supernova, as well as some of the results from the radio analysis that we did. So it was mentioned before briefly, but this is a type 1c broadline supernova. This is the type of supernova that's usually found in association with long gamma ray bursts. And from the spectra, we see that there are clear signs of iron 2 and silicon 2 and these broad absorption features that exist in the spectra that are blue shifted to pretty high velocities between 15,000 to 30,000 kilometers per second. And the only other X-ray shock breakout event that was discovered was actually a type 1b supernova. So that was supernova 2008D, and that was a unique event because it actually transitioned from a 1CBL to a type 1b around peak light. This is different because it stays a 1CBL. And we see a near-infrared spectra on the other side over here. And in these near-infrared spectra, if there is helium present, we'd expect a 1 micron feature as well as a 2 micron feature in absorption. But we do see evidence of this 1 micron feature. This 1 micron feature isn't necessarily just due to helium. It could be due to blending from a couple of lines, including carbon and magnesium. The fact that we don't see a 2 micron feature here that's significant tells us that there's probably no helium in this explosion, at least for the most part, but we can't definitively say that. So now moving on to the optical photometry that we got a really nice data set using ZTF and a lot of other telescopes within our collaboration. And we did some light curve modeling using Nikhil Sarin's code, Redback, where we kind of looked at all of these different scenarios shown here. So kind of TLDR, the biggest thing that we find is that a simple Arnett model, which is the usual model that is used for sort of modeling these sort of strip envelope supernovae, is not able to characterize the light curve well. We really need to see the radioactive decay of nickel in addition to some sort of CSM interaction that is able to reproduce the light curve, because this light curve has a fairly rapid rise when compared to the rest of the optically discovered type 1c broadline supernova population. Here we see some of the light curve properties, some of the supernova properties with respect to the optically discovered 1c broadline supernova population, other FXC supernovae, GRB supernovae, etc. So for the most part, this seems to be a pretty normal type 1c broadline supernovae, other than the fact that its rise time is pretty rapid compared to the rest of the population. And yeah, the paper goes through all the different scenarios that we model. So take a look at that if you want some more details. So this is a really nice schematic that Jillian made that shows sort of the progenitor scenario that we envision. We think that there was a Wolf-Rayet star that had some pretty significant mass loss before it died, leading to a dense CSM surrounding the Wolf-Rayet star, which is either a slightly inflated envelope of the progenitor or a slightly extended CSM. This is where the X-rays come from, where the shock is breaking out of. Then we see that a little bit further on, there's also another additional CSM component. And this is when the optical, where the supernova ejecta interacts with this additional component, in addition to the radioactive decay of nickel, which creates the optical supernova light curve. And further on, we see that there might be some more evidence of a more extended CSM because, and we would be able to probe that if we had radio data. And we have I think there's supposed to be a slide with the radio data, but it's not here. I think Brendan's going to go through some of the radio data that we presented in our paper, so I'll just leave it up to him. But what we saw in our radio data was that there was no detections. There were detections, but it was likely due to the host galaxy, and we were able to get really good constraints. And the biggest thing that we find is that radio emissions similar to supernova 2008D, the only other X-ray shock breakout event, was able to be ruled out. And we get some nice constraints on the CSM and sort of the mass loss rate of the progenitor that we could have if we were to have those radio non-detections. So yeah, I'll leave it to Brendan now.
Thanks, Gokul. And somebody's going to have to hit the slides for me to change them. Thanks
I
for
apologize
accommodating
for the lack of
virtual
the
talk.
radio slide.
Perfect.
Hello, sorry. Can you hear me? I will switch your slides, Brendan. I just wanted to say I'm sorry. Somehow the radio slide didn't fit in. Apologies. Brendan, please go ahead.
Okay, cool. Thanks. Thanks everyone for all these great presentations on this really fascinating event. As Daniele said at the beginning, this is really the third closest high energy association with a 1CBL supernova. And because of that, we can take great observations to low luminosities. And Gokul and some others hinted at it already, that there is no non-thermal component seen in the X-rays, nothing seen in the radio. And usually when we have these low luminosity, high energy associations with 1CBL supernova, we do see this non-thermal component. And you see in purple here on this light curve of X-ray luminosity versus time, some of these low luminosity GRBs. And we use Chandra to rule out that these, an X-ray afterglow similar to these events. And the EP FXT observations at early times, those upper limits that we saw before, are also very, very constraining. In general, though, these observations and the EP FXT observations can rule out the X-ray afterglows of all known gamma ray bursts except for GW 170817, and can also exclude the afterglows of other EP fast X-ray transients, which is really interesting. Daniele, could you hit the slide? And here's a radio slide. Gokul was talking about this, and in Jillian's paper that Gokul was talking about, there are deep VLA observations that I wanted to highlight as well. That detect a constant source that's likely due to star formation. And basically you can get some upper limits from this source not being variable. And here you see the radioluminosity versus rest frame time. The upper limits are these downward red triangles. And basically all of these exotic transients are excluded, including all of the low luminosity radio afterglows. And as Gokul also said in some of the other works, all of the people talking today have radio data and present similar constraints to this, and they can rule out supernova 2008D as well, which is really, really fascinating that you have this other shock breakout event that had more fast-moving relativistic ejecta than this 1CBL associated event did. Can you switch slides? So we place constraints on the relativistic outflow using these X-ray and radio upper limits. Basically, we assumed that we had to have a high-density wind environment due to this pre-explosion activity and CSM that James was talking about. And we show here on the right the allowed region of parameter space. So this shaded region in the bottom left corner in Lorentz factor on the y-axis and isotropic equivalent kinetic energy on the x-axis, basically to not be detected by all of these radio and X-ray constraints requires that you have this really low energy or low Lorentz factor outflow, which is completely different from what we've seen from some of these other 1CBL explosions that produce gamma ray bursts. So we interpret this to mean that there's a choked jet, that there was no successful relativistic outflow. Of course, if you have a very low density environment, which would be at odds probably with the mass loss that this star was showing in the Pan-STARRS images, then you could still possibly miss this. But in any case, the X-ray and radio observations rule out the afterglows of all of these other GRB-associated transients. So that's one of the interesting things here. Okay, that's it for me. Thanks.
Thank you.
Hello, everyone. I'm the last. Sorry. Hello. I'm here speaking as the second author of this last paper here in this series. And so our paper actually does two things. We also do a lot of supernova modeling. We actually have a beautiful spectral series. We do modeling of the actual supernova, the ejecta, and the mass of progenitor and things like that. But our distinctive thing in the paper is dealing with the host galaxy. So we heard something 2 talks ago about this. So we have this beautiful galaxy, a dwarf galaxy, low mass galaxy, 8.4 solar masses, stellar mass, about 8.5 kiloparsecs big. Maybe a bar, probably not a spiral galaxy, but some kind of dwarf galaxy. And the supernova is in this really bright, giant blue region, which actually some thought originally it might be actually a satellite galaxy, which is not. And So the interesting thing is that we have data that that separates this blue region. If you look at it in more detail, it separates into two star-forming regions with a distance of about 134 kiloparsecs. And the supernova is like on the eastern edge of the what we call star formation region west. And that region is extremely young. So this is an X-shooter spectrum, which we did not publish in the paper. And you see the Balmer lines, which very quickly, if you have any kind of a bit older stellar population, get to be in absorption. We have the entire series up to where it basically blends into where the Balmer break would be, if you have a Balmer break. We have them all in emission, and we have some other lines that are indicative of a very, very young stellar population. And so what I found very funny is that this galaxy has basically the same size and a very similar mass. It's slightly lighter than the Large Magellanic Cloud, and the Large Magellanic Cloud also has a giant H2 region. And so if you turn around the LMC a bit, you have kind of something. So this is the LMC twin at 150 megaparsecs. Okay, so what makes it exciting in our paper is that we actually obtained MUSE data, not just the normal standard observing observations of 0.2 arc seconds sampling, but we also have narrow field mode data, which are 8 times better. And so who knows me is like, I always like to have any kind of host that you resolve. I want to have IFU spectra. In this case, it is not my fault. So the problem was that in the beginning, we didn't know what was, so there was a transient, a high energy transient, there was this blue star forming region. Is it varying? Whereas the supernova, so better we take a spectrum of the full galaxy, also because then they can do more stuff. And so then actually in narrow field mode data, we also obtained because we wanted to pinpoint the exact location of the supernova compared to the rest of the H2 region, as we knew that. And so as I said, they separate into 2 regions. One is about 10 times brighter than the other one, the giant one. And this giant H2 region is the most metal poor part of the galaxy. So you here have a map of metallicity. The giant H2 region is up here. So this is always the same size. It has very high star formation rate compared to the rest of the galaxy, although we do have some star forming regions around, and we basically have no extinction. And so this is just to say that we are very sure that it's not a separate galaxy, because some thought it might have been a satellite that's independent of that host galaxy. That host galaxy is basically face on. So any satellite would have to have some kind of velocity difference. If you look at the spectra here, for example, at N2 in H alpha, you see, so you see the lines drawn here, they're all exactly at the same position. So these are extracted integrated spectra of the narrow field region. This is the integrated giant H2 region. These are some other regions of the galaxy that are exactly the same redshift. And so the metallicity of the giant H2 region is quite low, lower than what we've usually seen for broadline 1C supernovae, lower than what we have usually seen for GRBs. And it also has a very high star formation rate and a very high specific star formation rate, as you can imagine. And so if we compare that, okay, some of these things slid a bit around. So the circles are not where they should be. So we have here a comparison in the mass metallicity relation with other samples. So this is the probable ones here are long GRBs, which are associated with broadline 1C supernovae. Some other 1C broadline supernovae from the Moja sample, which are here in red. And these are superluminous supernovae, superluminous supernova type 1, which we kind of know that they are not the same population as, and they probably don't come from the same percentages as gamma ray bursts and thus broadline 1C supernovae. But we are more in this region here among the superluminous supernova type 1 at very low metallicities. You see, if you take an integrated spectrum of the host, which is interesting if you have to observe these kind of things at high redshift, you would get a very similar metallicity in this case because the star-forming region is so dominating your spectrum and the luminosity of your lines. And another interesting thing, unfortunately, it's shifted a bit. So here's a comparison of the metallicity in different spaxels of the host compared to the specific star formation rate, weighted by the luminosity. And so this tail out here is the giant H2 region. So you see that the giant H2 region has a basically uniform metallicity. Of course, it has different star formation rate because the star formation rate is measured from H alpha, which is nothing else than the kind of ionizing radiation that you get, which of course depends on how many stars you have in exactly that spaxel. So that's interesting. So you have this giant H2 region came from some starburst. As I said, something probably similar to 30 Dorados. And yeah, the interesting thing is that the environment looks a bit different and much more extreme than what we would have expected from other broadline 1C supernovae. And with this, I give to the last speaker, which is different.
Hello, everyone. My name is Hui Sears. I'm a postdoc at Rutgers University working with Sarab. I'm here to show you some unpublished in-prep JWST spectra of 26 GZF. I'm working in close collaboration on these spectra with Manisha and Lindsay, who I show in the top right. In this plot, I have compared GZF in black to another 1C broadline supernova 24 ABUP, which is at redshift 0.006. It's published in Manisha's recent paper on the archive. What we see in comparison is this really bright mid-infrared excess over on the right in comparison to 24 ABUP. I'm still working on the modeling. We're still trying to figure out what exactly this is, but it's fit pretty well by a dust profile. And we also see several narrow features in the black, which are associated with hydrogen lines. So we're associating those with the underlying / nearby star-forming region. And that's all I'll say about this right now. Thank you.
Well, thank you so much to all the speakers. We are a bit late with the session, so I had highlighted a few open questions, but I think we should take questions from the audience and have more. So if anyone has a question, please go ahead.
Okay, I start with, can you recap why we are sure that there is not an off-axis afterglow from possible off-axis gamma reverse? So a gamma reverse that we are seeing totally off-axis. Are we sure that there is not an off-axis afterglow?
Brendan, do you want to take
and why?
this?
Yeah, sure. Sorry, there we go. Yeah, no, that's a really good question. And so I think the thing is, it depends on whether you assume that this is in a wind environment or an ISM environment. So if you're in a wind environment, which seems like this has to be given the mass loss of the progenitor star, then at large off-axis angles, since the density is so close to the star, the large angles decelerate rather quickly as well. So you don't get this delayed GW170817 like afterglow shape where you could miss it in these observations. So it really comes down to that assumption for the density. But as you can see here from this plot, that the assumption or that at going to further off-axis angles, so these different lines and colors are 2 times the core, viewing from 2 times the core, viewing from 4 times the core, and viewing from 6 times the core. And you have this really weak dependence on off-axis angle in a wind environment. So that's it depends on that assumption there. Yeah.
But I don't know if I'm allowed to make a comment. But I don't think we can rule out that there was a jet off axis. Some of the papers have as a function of a limit constraints as a function of the angle. But the point is, if a jet is very much off axis, then the X-ray emission seen by EP is not that. We are not seeing that. So every supernova could have sorry. Every supernova can have a jet off axis that we don't see in the first years or after the
fine. So, but
explosion.
EP they didn't explain as an off-axis plane as thermal, no?
Yes, exactly.
So yeah.
So there could be, I assume there could be potentially, as in every supernova, there could be a jet that we don't think.
Yeah. Okay.
But it simply doesn't really, like, the progenitor may be still capable of producing the jet, but it doesn't affect the emission that we have seen.
Yeah. Oh, this is okay. Just to have a clear picture that is not impossible that there is the jet.
No, there's way too much parameter space, right, to rule out everything completely. So you have to make some assumptions and then say what your allowed parameter space is based on those assumptions. Yeah.
So just to follow up on this point, I think what Brendan was pointing out, theta V over theta C, it's 6, but that's quite small, Brendan. I mean, if you would need highly off-axis angles, right? We had for 17 roughly similar theta V, theta core of 5. You would be like, why didn't you try like 10 or more than 10, right?
Yeah, so I could make this plot for larger angles, and I think the dependence is quite weak if you assume the density is high. As soon as you start to drop the density lower, then yeah, you could go far off axis. But
so
I can make that
other
plot
thing
and send it to you.
is anybody monitoring in radio the source? Maybe you would definitely, if there's an off-axis jet, you would definitely see it later times because it'll become more isotropic, the emission.
The answer is yes. People are monitoring this in the radio, but it's not been detected yet. The question right behind you, Win.
So this is kind of for everyone on the panel, but and maybe it's related to the second question on the, like, I don't know, prompt questions, but I guess, what do you all want to call shock breakout? Because you have a number of EP events that are 1Cs with X-ray flashes, but for this one, this is shock breakout. Why? Why is this one? Like, you're going to find, I understand the argument is, oh, it's lower X-ray luminosities than the last EP events, but it's a 1C in a parameter space that we don't know at all. Like, so I don't know, like, what do you think is the future of understanding the definition of shock breakout in the regime of relativistic supernovae, and how do you want to see it proceed?
I think there was debate when writing the EP paper, and so it's not a breakout from the surface. So I think that's different from the classic definition. And if there's a shock, the breakout from some material can be the new definition that can fit into that. But if not, if we like there, that depends on the definition. And for previous events, there's some like we can fit the prompt emission with power low, so that means it's not thermal. And some of them we don't exactly know, so we cannot claim it's like a definite shock breakout. But for this event, the power law like basically just fail. So it's different from the previous like 3-4 supernova associated EP events.
I also have sorry, can I say something too? I actually do interpret those other EP transients as shock breakout win, and I totally agree with you that we need to come up with a better definition. I mean, I think going back to 2006 for GRBO 60218, that was also called shock breakout. And it really comes down to whether you consider it relativistic or non-relativistic shock breakout. And I think the difference between what we're seeing of all these other EP events and low luminosity GRBs is really just the amount of relativistic material that's getting ejected and whether that jet was successful or choked. The low luminosity GRBs that we associate with relativistic shock breakout have both thermal and power law components. So it's totally true that this is the first 1CBL where we don't have this prompt power law component, and that does make it different. But I would consider all the others to be shock breakouts. And if you take a look at my paper, we do put it in the context of those.
Yes, I have a question for James. Yeah, you reported that you find in the Pan-STARRS archive data, you have recurrent variability before the supernova explosion, and it's spatially and timely associated. Yeah, which I agree. But the point is, this source is 100 megaparsec away, so even your resolution, spatial resolution is 1 arcsecond, you can only resolve the KPC scale space. So is a star-forming region. So how do you know this variability is coming from the star or not the entire star-forming region? Yeah. Because we cannot resolve the single star, even if it has some extended envelope. You only resolve KPC scale region. Yeah.
Sure. Yeah. So the argument is that there is some activity in the vicinity of the supernova, and it could be multiple stars undergoing some outbursting activity. But the argument is that because this is the one that exploded, it was probably the most volatile in the immediate years prior to the explosion. Some connecting of dots there that maybe all of the variability does not tie to, but I think there is an argument for at least some of the activity to be linked to the star before it exploded.
Yeah. May I say something to that? Because I have been dealing with similar objects 11 years ago. And so I have to say, when I saw the paper, I have severe doubts on the pre-explosion activity. I don't exactly know what is going on, whether you have some issue with your photometry or not, but just looking at the physical implications of that pre-explosion activity, I have my severe doubts. Because if you put that, for example, in an HR diagram, or you just look at the luminosity, because that thing is at 140 megaparsec, that's very far to detect any pre-explosion activity of anything, because that has to be very faint. And so if you put that in luminosity, that would be any of these things that go above the whatever level you said would be brighter than an Eta Carinae great eruption. And there is no indication of for the star being something that has like 100+ solar masses. So we have an estimate of, let's say, around 30 solar mass, 0-age main sequence of the progenitor. So I think just from looking at the luminosity, it's rather unfeasible that this was pre-explosion activity of that star.
Sure, yeah. I mean, so I'm not an expert on this stuff, but it's not obvious to me that you need multiple solar mass ejected to reach these luminosities. I mean, this is a very uncertain system. It's plausible that is this working? Yeah. Oh. Sorry? Oh, sorry. So I was just saying I'm not the expert on this, but it's not obvious that that's a definitively true statement. It's plausible that some subsolar mass amount of ejecta colliding can reach the energies and luminosities you need to power this type of thing. It's not clear to me that this is a well understood type of system or type of interaction. So I don't know that you do need to invoke tens of solar masses of ejecta to get to that luminosity. It's true, but I mean, if you ejected, on the order of 1/10 of a solar mass or something, and you have multiple shells that are colliding, I don't see any. I don't see any obvious reason why that couldn't be invoked to explain the luminosity. I mean, it's comparable to the great eruptions of 1961 V or something, right? So it's on the order of that, and that has been seen before.
As far as I remember from the plot, it is even brighter than that.
It's brighter than that, but it's...
And 61V is a very extreme system,
sure,
likely.
But there are other events comparable, again, within a mag. A factor of a few, I mean, to an astronomer, sure.
Yes, but a factor of a few in magnitude, unfortunately, is several orders of magnitude in luminosity.
No, a factor of just one mag or something more luminous than the other objects on the order. So it's only a factor of... I don't think we're in a parameter space that is completely extreme relative to what has been seen before. And what can be explained physically. I think it is... A lot more work is needed to explain this more...
Yes,
but it's not obvious that you need to invoke 10 solar masses of ejecta.
And I'm sorry it hasn't been explained in the paper. I've been reading it multiple times, and there has been no explanation on that. I was lacking that.
Well, maybe the reviewer will agree with your points, and we can add some additional motivation or something. Sure.
Well, thanks.
I would just give one comment that the easiest check is to wait. I think that's a result that deserves to report to the community. And another thing we should do is to wait to 1 to 3 years later, and we see whether you have the variability at that region. If so, we know it's uncorrelated to the supernova. But if there's no, maybe we know there's some correlation to the supernova. Yeah, that's just comment. Yeah, thank you.
Daniele. I'll take this last note to say, given all of this interest and scientific discussion on this object, if you see proposals asking to continue to observe this object, perhaps you should approve them in future observation cycles.
I guess it's we all share your request with our own proposal. So anyway, I think we have one last task. We should thank the speakers for putting together this session.